Okay, so we'll be starting now. So you can go ahead.
Okay, so I'm audible, right?
Yeah, you're audible.
Okay. So, hi, my name is Som Tambe. I'm from the Department of Aerospace Engineering here at IIT Kanpur. And today I will be giving a talk on few shot learning, which has been organized by the Brain and Cognitive Society, IIT Kanpur. So, let's begin. So we'll start with the basics. I don't want it to be intimidating to any person. So I have made it in such a way that each and every person can take out some or the other thing from this talk. And if you want to know more, then that is dependent on the curiosity of the person. Then he can always contact me. So we'll begin. Suppose you are given an object like this and you have probably never seen it in your life. So as we can say, this is a scooter, but now, for example, you have seen it for the first time in your life. So we as humans can derive many different things from the given as object. We can derive various aspects of the object, such as the object has a steering wheel. We can also observe that the object has a handle, and we can also observe that the object has two wheels. Those have been connected by this base plate. So the combination of all these things make this object. We can derive even more things out of this, but let's keep it to this. So let's talk about the extent of our human imagination. Humans can imagine a whole lot of stuff. For example, given the different parts in that object and some other objects too, we can mix and merge different units of all those objects to make a whole new composite structure. For example, this object consisted of a handle, a steering wheel, as well as two tires. This is a normal motorbike which consists of its chassis, the two wheels, an exhaust, and a steering wheel. And this is a motorcycle which has a seat on it. So, for example, if I think that I want to combine the chassis of the motorbike with the wheel of a motorcycle, and I want to have a person sitting on it, I want to imagine myself sitting on it. I can do that, and here is what my the image in my imagination would be ideally. So now, for example, considering the first slide, the scooter you have been given, you are asked to find a similar looking object in the among various objects given to you. Now, as we see over here, we've got a motorcycle, we've got a biped, we've got a car, we've got a Harley Davidson like thing. We've got a normal cycle. We've got another variant of a moped. We've got another variant of a motorcycle, and we've got another biped. So, what would be the similar object as compared to the first slide? So, if you observe all these, if I observe the steering wheel, these two objects have the steering wheels as well as these bikes. If I talk about two tires, this object, the bikes, the cycle, and the biped, all of them have two tires. And if I talk about both the tires being joined by base plate, I will only get this one object. So it might seem common sense to you, but you've only been given one example of that object and you are guessing it right. And you're not taking any effort in guessing it right. So that is going to be the crux of our talk today, and I'll give you an overview. So, machine learning models are basically matrices. All of them have initialized values to the values are randomly initialized at the beginning of training, and when they're untrained, they're literally useless. So, I'll give you an example. What is literally what I refer to as literally useless. If I take a generative adversarial network, which is an example of a machine learning model, combination of machine learning models, and if I just pass some random noise through it, I will get this image what you see in the right. So this is, as you see, it's completely noise. It's a 28 by 28 grid of grayscale pixels consisting of absolutely random values that make no sense. You cannot derive a digit out of it or anything as such. So now I shall give a brief introduction to how models work and how they train, how machine learning models work, especially deep learning models. So here what we see in front of us is a vanilla neural network. As you see, it has the input vector you give from here. It also has the output vector that you get after passing the input vector through the machine learning model. And these are the weights of the layers in between. So as you see, there is one input layer and there are three hidden layers over here. So basically, hidden layers are, you can consider them as the two hidden layers as a big matrice. For example, if you have a hidden layer of 8 elements and the second hidden layer is of 13 elements, so the matrice will be of a shape 13 by 8, and that will give me the a matrix multiplication with a vector of 8 elements will give me a 13 element vector. So that 13 element vector will be passed on to further matrices as such. So this is what a machine learning model, a vanilla neural network, as you would call, consists of. Vanilla is referred to as just a plain neural network with no complications as such. And the inner layers are trainable. So the inner layers are the essence of a model. We use gradient descent to train the inner layers. So let's talk about gradient descent. So here is what you see, a graph on the three-dimensional Euclidean plane. So gradient descent is the most commonly used algorithm to train neural networks. And it is an iterative optimization algorithm which aims to minimize a given objective function. And it's not always guaranteed to reach the minima. So what I mean to say is, now this graph you see over here, our consider the machine learning model as a function which a function f of x as you take in math, and it gives you an output g of x. So here, if I'm inputting a value of any given value, and if I find the for a given set of weights, I'm just mapping the output. So not the output, but an, an objective function to it. So I need to minimize an objective function. How do we train the inner layers? That is only by minimizing an objective function that exists. And the objective function is a very simple example of an objective function is the least mean squares error function. So basically, if you are performing learning with given examples, if I have a neural network, I want to train it to recognize digits. So I have the digit images and I have the data about what the digit exactly means. If I have a digit 9, I will have a digit 9 in the training set to verify my hypothesis with. So that hypothesis subtracted by the a very simple example of an error is you subtract the expected value and the output value with each other, and you take the modulus of it. And what you would want is that every iteration should minimize that value, right? The error rate should be minimized so that my classifier works properly. So for example, now for a given set of weights, the graph looks like this, and we are over here. So what we need to do is we need to go to the minima of the whole weight plane. So that is a bit difficult to visualize actually. And there are also concepts like saddle points, local minimas, and global minimas. So those are some problems that these convex optimization problem algorithms encounter. And just to show you a meme, uh, why large amount of training examples are required, and if you don't give a lot of training examples, uh, few short learning can happen like this can happen, like the mom is showing the baby, this is daddy, but the baby starts finding daddy everywhere. So this is the correct daddy, but these aren't correct daddies. So this should not happen. We need to find the correct person. We need to find achieve our objective. So that is our aim. So this is I'm giving you an example. Now this is an input image of a digit 5. And here is our neural network. I feed this to this. Now, how do I feed this? Because it's an image, it's not a vector. There are many ways to feed it. First, it's a 28 by 28 image. I can flatten it and feed it as a vector. So 28 by 28 is 784. I can feed a 784 length vector inside. And the output should be a 10 unit vector, which gives the maximum value of the vector would exist at the point of maximum confidence. For example, this digit is 5. So the sixth index of the vector would have the maximum possible value. So as we are seeing over here. So this digit classifier trains with a minimum of 10,000 examples to give useful results. And that is a large number of examples for 28 by 28 images only. Now 28 by 28 pixels are, it's like very small. Nowadays we are accustomed to using displays of large pixels, and we have images of 4K quality and 1080p and whatnot. So just wonder the amount of data we would require for those, for training something like that. I mean, for example, an object classifier or something like that. And in general, learning is a difficult task, and you're not guaranteed to reach the optimal solution using any convex optimization algorithm, at least yet. So that is a problem that plagues a lot of aspects in machine learning. So our talk involves one-shot learning. So how, according to you, would it be possible for a model like this, as I discussed previously, to perform good when provided with a single example or a few 10 examples? For example, you're providing some 20, 40, 60, 80 examples. How would it be possible? And now consider the number of classes were only 10, because the digits those exist are only 10. All other numbers are formed by the amalgamation of one of those digits, or two or three, n number of digits. Here, if you have n number of characters, for example, 1,000 letters or 1,000 characters in a language, so the sample size is increased to 1,000, and now you have very less number of images. How would you train it? And how would you expect it to perform? So let's discuss. So right now, I will give you a brief introduction to the Omniglot challenge. So whatever you see here, I'll explain it. So it was a challenge with 5 different tasks introduced in 2016 by Brendan Lake and other scientists working at the New York University. At that time, Brendan Lake was working at MIT, I guess. But and it was released with a dataset which is popularly known as the Omniglot dataset, which contains 50 alphabets with a background set of 30 alphabets and 20 alphabets in the evaluation set. This totals to 1623 characters with 20 examples for each class. So I'll explain you. What is an alphabet? For example, all the characters of English language are an alphabet. So I have 26 characters in English itself, or the Roman script itself. So that would count as one alphabet. So one alphabet has 26 of its classes. Now there can be examples like Devanagari Lipi or Gurumukhi or some Tamil script or Kannada, which contain different number of letters, different types of characters, and the there can be a lot more examples. So like that, they have compiled a set of 50 alphabets. You can consider them as 50 languages, and multiple and only 20 examples in each of the character in each alphabet they have provided. So for example, I have the character A, or if you take in Devanagari, it can be K or K. It will only have 20 images of the character in that class. So this is the data set. And as compared to the common MNIST data set, which trains on only for 10 digits, each of the digit has 6,000 examples of 28 by 28 images. So that is the difference between the Omniglot dataset and any other dataset for use for image classification or computer vision models. And along with that, you are given the stroke data of each and every character. So what you are given is the x coordinate, y coordinate, and the time coordinate of each and every character. For example, if I take a curve, there are multiple points in which I have to lift the pen. If I draw a vertical line, then I draw a horizontal. Sorry, if I draw a horizontal line, I start with drawing a horizontal line. Then I draw a vertical line, and then I draw the curve that exists. So there are three strokes I used in this. So all the data of those strokes is given to me. So I have to utilize that data and solve these challenges. Now, what are the five challenges? The first challenge was one-shot classification. For example, I'm given this, and I have to find another example of this in all these examples, all these given examples. That was one task. Another task was parsing. So what is parsing? Parsing is basically I have the stroke data of each and everything. As you see, here is the H character. There are 9 examples of H, and this is the way the humans parse. The red stroke first, then in this way, and then I draw a curve in this way. And that is given for each and every curve, each and every character example they are given. So the machine has to decipher the way in which the humans have passed to get that character. So this is the way Brendan Lake's Brendan Lake had performed in his paper in the parsing task, as you see. So it's quite impressive. And the third challenge was generating new exemplars. So that was about new. It's like you have to distinguish if a character is human or machine. You're given two sets of the characters, different instances of characters, and you have to det- uh, classify whether they're human or machine. Generating new concepts from types. What does that mean? If I have curve has a horizontal line, a vertical line, and another curve. So I have various such alphabets across 50, various such instances across 50 alphabets. With all that data, I have to learn what kind of strokes are used in across all the languages, and whether I am being able to make completely new character, or a machine generated instance of an existing character. So that is another task. And the fifth task is also the same, but it has a bit of less constraints, so they can generate completely new characters also, but it's a subset. So let's move on. So the first paper in this field was that of Bayesian program learning. So this is an extremely popular paper by Brendan Lake and his team, which makes use of Bayesian program learning. And it uses the Omniglot dataset, and it uses generative models which sample new concepts by combining parts and subparts. And if you observe, then what they have did is they represent each of these types as newer generative models. So I'll explain to you. This is the raw data I have been given, and if I divide it into, if I go backwards this way, I have this stroke and then this stroke. Now these are the primitives that, as I said, those can be derived from various languages. These can be the subparts I've made. For example, the curve. I can adjust the curve a bit to, I can generate some randomness in it to make it look as a new character. Then we combine these curves to make parts. Then we get a then we combine different parts to get the object itself. So for example, I can have this stroke. I have this stroke, but this can be divided into more subparts. So these two combine to get the character we want, that is oo. And this is here, there are many examples for characters from other languages too. And as you see, this character can be generated using this. And in this way, they have hand engineered each and every part of that to achieve the task that he had set in his paper. And here I'll introduce you to prototype based classification. So as you see on the screen, if I'm given these two footballs, I know they are the same. If I'm giving a football and a crocodile, they are obviously different. Two elephants are also the same, but an elephant and a crocodile is different because they both of them are different characters, creatures in themselves. So even for example, if you take a speech model, a cow and cow is the same. A cow and cat cannot be the same. Both, if both are cans, then both are the same. But a can and a cab is not the. And in that way, there are verification tasks to train. For example, I want to train it. Sorry. So these are the verification tasks. And what are the one-shot tasks? Basically, I want to classify this ball into the other objects, one of the three objects. So of course, this will go over here. It's a basketball ball. And cob needs to go to cob rather than going to cot or cob. So that is what I want to aim to achieve. So that can be taken as a basis of one-shot learning. So there was this another paper known as, which introduced Siamese networks to the world. So as you can see in the image, you can get a fair idea of what they are doing. So they're using the embeddings generated by two different neural networks, and they are using those embeddings and combining. They are looking at the similarity between those two embeddings. If I use cosine similarity to get the difference between two embeddings, if I want to check if they are approximately of the same class, then the vectors generated by the neural networks, if they're trained on that, they should be they should give a value tending to zero. Basically, it's a problem. You can extrapolate the problem to n dimensions. For example, if you have points given in two close points given in the two-dimensional plane, those points can be measured as close if uh, the vectors are near to each other, the coordinates are near to each other. So you use that concept to and extrapolate it to n dimensions to check if those vectors are near to each other. Because if they are of the same class, then the generated output should be near to each other. And the inner layers of both the neural networks share the same set of weight matrices, and it's trained using backpropagation. And the setup that I mentioned before, if if I, for example, I'm passing the image of a crocodile and a ball, so they should be different to each other. So the cosine distance outputted by them should be 1. It should be false. The output should be given as false. So on the basis of that, the networks are trained. So here I'll give you the performance of the existing networks, and I'm sorry I couldn't make a graph out of it. So I'll explain each and everything. Humans perform, if you take the original omnicolor dataset, humans performed with a less than 4.5% error in the one-shot learning task, and this is the original dataset. If you observe Bayesian program learning, it performed at a error rate even lesser than the humans. That was 3.3%. And if you take a simple convolutional neural network to check the results, it performed at a error of 13.5%. And here for Siamese neural networks, what they had done is that they had augmented the data. Basically, you create new instances of the same data by manipulating it in a few small ways. By, for example, you can put a mirror image of it and check the similarity of two mirror images. So, for example, you have two images. You take the mirror image of both the images. The data gets doubled. So that is how you increase the data. And using augmentation, Siamese neural networks got an error rate of 8%. And these are the results of the literature, the studies, those were done later on. And we won't be discussing that in this lecture. So what our project had done, we derive motivation from Bayesian program learning using the parts concept, and from prototype based classification by using the generated embeddings to generate a similarity model. So I'll explain you. The first question should be, why not use Siamese or Bayesian program learning? Because BPL hand engineered each and every part, and this could cause problems while scaling it at larger levels, or applications other than language, like the one I illustrated at the very beginning. So if you have different type of data, if you're not given stroke data and such, then it can prove to be a problem because it was hand engineered at each and every part. So that is one of the reasons it performed well, I guess. Siamese neural networks generate end-to-end embeddings and do not capture the advanced methods we humans used for breaking up the characters into even smaller primitives. So we have characters, we can derive a lot of information from a given character. Now we don't know the stroke data from any character over here. So I can easily derive that this stroke can be used, this stroke can be used, and this stroke can be used. But the Siamese network cannot do that. It is only trained on the on the topic of one shot classification, and we need to we thought that we need to make a better system. So let me give you an outline of how our project goes. So what we do is that we first convert all the stroke data to a 25 point spleen. So the stroke data is often non-constant length. It can vary from even one stroke. If I'm putting a dot, a bindi over ka to put the matra, it can only be a dot. It requires only one point. So the stroke only had one data point in it. If I take ka, then there are multiple data points. It can exceed the length of 50 if I'm taking a bit of time to draw it. So we had data which extended to the length of 200 and something for the strokes, and we all wanted to bring it to some constant length. And a spleen and fitting the data to a spleen is a very good way to do that. A spleen is basically you fit the data to a polynomial. Here we fitted it to a third degree polynomial for for strokes greater than a certain length, and the rest we used some other technique. So what we do after that is we use all that 25 point spleen data, we flatten it, and we generate an n-dimensional vector for each and every stroke using a VAE. Now, what is a VAE? A VAE is a variational autoencoder which uses two networks in parallel. So I will explain what the concept of VAE in the coming slides. Then we use clustering to have an insight on the latent space learned using the VAE. Then we created a one hot vector for each and every sample in the dataset using the latent representation of their strokes. So for example, I'm given the curve in curve. I use the n-dimensional vector that is generated by using the VAE, and using that the data based on clustering, I form a one hot vector of each and every character. The character is a bigger part of the strokes. A character is a combination of multiple strokes. So I use the stroke data to get a one hot encoded vector for each and every character. So that the what will it mean? It basically means that I have a vector which lets me know it's letting me know the strokes those are present in the character. Then I use a C convolutional neural network to perform supervised learning on the characters and their one hot vectors that I have produced. And now, what is this CNN useful for? I can use it for two purposes. One is the one-shot learning application, and the second one is for classification purposes. So let's move forward. As I said, we use variational autoencoders. So here is the example of a VAE. So as I said, it comprises of two neural networks. The first one is known as the encoder network, and the second one is known as the decoder network. And the input, basically you are given a probability distribution. All your data is a distribution over over something. For example, as we see this image too, there can be multiple examples of this too written in different ways, but they all same they all denote two only. So we can we can assume it that the input is some variable x, and this encoder network is learning the latent representation of known as z with respect to x. For a given x, it's learning the hidden hidden representation of it. So what it does is encoder and decoder are two plain neural networks. What the encoder does is that, for example, I'm inputting a 10 length vector. I can decide on how what should be the length of my hidden variables. For example, if I take the length of it to be 2, the encoder will output me a 4 unit vector, of which the first 2 units are the mean of the distribution, and the last 2 units are the standard deviation of the distribution, or at least I'm assuming it to be that way. And using that, I can sample another two-dimensional vector for that thing, for the input. So the output of the encoder, as I said, it's divided into two parts, and the as I've said, so this is wrong. Sorry, this should be standard deviation, and the decoder is another thing, another vanilla neural network, takes the input of the which takes the input as the output of the encoder, and it reconstructs the given vector. So what we have to train it is on reconstructing the input vector. So it is a kind of unsupervised learning, because you don't need the data of what the number means. You don't need the data that this image denotes to for training this network. So it's a very popular method of learning probability distributions, and let's see how we have used it over here. I will illustrate the use of autoencoders, and to show you something interesting, if you train a similar autoencoder network on the MNIST dataset, MNIST dataset is the digit dataset from 0 to 9 with 60,000 total samples, then you can get a representation like this in the two-dimensional space. If I plot the hidden variable that is generated by the encoder network, and as you see the different colors used for these, you can see that there are different areas in which only one exists. For example, one exists only over here, zero exists only over here. So these are clusters of data. You won't find any randomness. As I said, the concept of Euclidean distance remains the same. If there are two samples of one taken, both of them will be over here only. They will be near to each other. If I take a sample of something like phi and 0, phi is over here and 0 is over here. So the Euclidean distance between them is large. So they are unsimilar. So this is what we see in when we plot and when we plot the output of the hidden variables. And if you use something like an adversarial autoencoder, which is a better form of an autoencoder, it lets you learn fit your data to a given Gaussian distribution. So you can get something neat like this. So as you see, this is still messy. So here I get 10 distinct classes of those digits. Those are each mapped distinctly. I won't see any mix and match of digits. It's a lot over here compared to over here. So here, as you see, the green part is overlapping. A bit of it is overlapping in the pink part. What is the green part? It is 7 and 4. So the the VAE network might have found some similarity between those, and it's learning it in this way. So there is a chance of classifying a 7 as a 4 or a 4 as a 7. Mostly it's a 7 as a 4 because this part is over here. But over here, it's a better distribution overall. So this is this is how VAs are used. So let's move forward. So for us, as I said, for each character, we had the stroke data and the time coordinates. And I will give you an example of K. So here is K. If I see there is one stroke over here, the second stroke over here, the third stroke over here, the fourth stroke is a curve, and the fifth vertical line. So all these different colored strokes are different colored lines are different strokes, distinct strokes. They're not the same stroke, or they're not the continuation of some other stroke. So if you see over here, as I've explained, since each and every stroke is of different length, we need to make it of equal length to make some use of it. So we fitted a third degree polynomial spleen, and as you can see in this image, the blue data represents the real stroke, and what we have done using the spleen, you can see this curve over here. So that is the spleen we have fitted over here. So this might be a larger number of points, but we will sample a lesser number of points from this spleen. But I will be ensured that I get a 25 length vector representing the same stroke that would have been represented in a large number of uh, data points. And after obtaining the xy coordinates of the 25 length curve, we normalize each and every stroke since we have to train a variational autoencoder. So here the stroke goes up till something like 80 comma minus 20. The coordinates of the stroke are 80 comma minus 20. Then there is a variation like over here it can be 20 comma minus 50. So the variation is large. So it's a bit difficult to train on such a huge variation. So what we do is we do the normalization trick, which is the x minus mu by sigma. You take the average of all the strokes, you divide it by the standard deviation, and you do it for each and every stroke. So what it does is, if I do x minus mu, it makes my character small. It will make it fit to a very small length over here, a very small square. And if I divide it by sigma, it is literally making it something like this. It's like the center of each and every stroke is the same. So if you see over here, this vertical line has come down over here, the horizontal line has come over here, and there is no character as such, you see. But that is what we need because we observed that it wasn't training that much better if I didn't do the trick. So this is what we get. And now after training the variational autoencoder, so what we needed was that the output of the normalized characters should be the should look the same as the normalized characters. Those were inputted. So I'll give you an instance of what was the output of the decoder. So this is the decoder output for this input after training 150 epochs. So as you see, the red line over here remains a very similar red stroke over here. The curve over here in orange also looks very similar. The horizontal line also looks very similar. And the green curve, which denoted the round, the bobbin curve, it also has been represented by another green stroke, which looks very similar to that, even if it does not look exactly the same. So it's an indication of successful training. And I cannot denormalize this because I'm basically losing data when I'm dividing it by the standard deviation. So I cannot place it to something that would represent k again, because that could be arbitrary. So that is one problem of this, but we don't need that anyways. We only needed the encoder network to learn the representation of the input strokes. So, as I said, there are multiple characters in different languages all across the globe having similar strokes. For example, the vertical lines, the semicircular curves. And we could use the decoder network to give us a latent vector for each and every stroke as such. So, what would be a benefit of getting the latent vector? It would be a two-dimensional vector or a three-dimensional vector, a vector of smaller size, which represents the same stroke, which is represented by 25 or even more in the given data. And on clustering these vectors, we can find how many different strokes there do exist. By clustering, we can observe how many different clusters exist. And in this way, we can create a one hot encoded vector for each and every character. What is a one hot encoded vector? For example, I am making a T. A T is a very simple character which has only two strokes. It is a horizontal line and a vertical line. So I can find clusters which only consist of horizontal lines and vertical lines. And if I found a total of 10 clusters, 10 different strokes in total in all of my data, I can mark a 1 over the stroke which is present in that character and a 0 over the stroke that is not present in that character. So the cluster index at which this stroke was present, I would mark it as 1. So there would be two ones in this vector. Out of a 10 length vector, there would be two ones for a T. This is just an example. There should be more, a huge length vector, a larger length vector for any character. And we could further use these vectors along with the images of the characters to perform supervised learning, to train another neural network, which basically trains it to give the stroke data of any input image. So if I have given another composite composite letter, if I mix and match any strokes and make something, then the CNN that I have trained could give me the stroke data for even that image, that character that it hasn't seen. So the embeddings would be useful overall for two types of tasks, as I've said. So here I'll show you the clustering results, assuming a latent space vector of 2 dimensions and 3 dimensions. So this is the data for clustering we got when we used 2 dimension. And as you see, we have kept the number of clusters to be huge. We thought that there are a huge number of primitives that should exist, about 200 or 250. So if you cluster them, they look something like this, with different colors indicating different strokes. And if you cluster a cluster, if you assume a three-dimensional vector, then the space, the plot looks something like this. Now the three-dimensional thing is not visible exactly because it needs to be uh, it needs to be seen physically. So it's like if you zoom in and zoom out, you will find some clusters. And as you see, the clusters were not distinctly visible. If you see over here, it wasn't a complete group of points over here, and then there were a group of points over here. So if you see, the cluster would have shared boundaries. So after zooming, you can observe that there are various clusters visible, but most of them shared their boundaries. And in a way, this implies that strokes are not the most primitive stage of characters. Strokes can be further divided into primitives. For example, we saw the U example. So U consisted of a three-like shape. So the three is the stroke of three is made up of two semicircles. So we could divide it further into two strokes, into two primitives, as we call it. Primitive should be the base unit of any character. So if we use these primitives and then feed them into the VAE, we can cluster them and get better and distinct clusters. That is our hypothesis. So this was all from my side, and the project repo is over here. And if there are any questions or suggestions, then I'll try to answer them in the best possible way.
Hi, can you go back to the performance slide?
Performance, yeah, sure. Yeah,
16th slide. Yeah,
this
so
one, right?
what
Yeah.
does the background set here mean?
So the background set is the set on which the characters are not trained on. For example, you have 30, the total data set consisted of 50 character, 50
Mm-hmm.
alphabets. It was divided into two sets of evaluation and background set. So 30 alphabets were for background and 20 were for evaluation. So you train your models and everything on background, and
Okay.
the other part of the data set is it's like unseen data. I want to
Oh, okay, okay.
use some characters from other language to see if if my
Yeah.
models are performing the same on them or not.
And it would be nice to see convolutional nets on the minimal background set one. I think the performance would be bad that way.
Yes, the performance is bad. I think we had implemented it, and it was something about 50% or even
Mm, yeah,
lesser than that.
makes sense.
The performance was not that good. Hi, I cannot hear your voice. It's a bit less.
Yeah, but your voice is too low. I guess you can use a headphone. That would be better.
Yeah, yeah, speak. I've increased my volume.
Can you go to the slide where you discussed few short learning like
Just a second.
verification and
Okay, okay.
yeah.
Yeah.
So can you please more elaborate more how we are verifying like how we are training the neural net to verify that these two are similar? Yeah, I mean I understand the cosine distance thing that you discussed, right?
Right.
So I was are you doing that? You have some labeled data set, right? And
Right.
then you
Absolutely.
train
Yes.
the uh, images sorry, you train the neural net to identify them as that particular object, right? And once the neural net is trained, you just use it for like the example you have showed here below,
No, I think that is
verification
the
task.
difference over here. The method of training is different. So it's like you have two different neural networks. Those are trained in the way that, for example, you don't have the data for the labels about them. But
Oh, so
sorry, wait a second.
it's like one or
It's not
zero,
trained
right?
in the conventional way. It's trained in a way like, for example, I have a set of, for example, I'm taking 10 classes and I'm scrambling them in any way. And 10 classes of each, and all the examples are equally distributed in each of the class. So
Okay.
now what you can do is form two copies of the same data,
Yeah,
and you
got
can
it.
randomize the order of both of them. You have the labels
Yeah, yeah, yeah.
with you. If
Yeah.
both of them belong to the same class, cosine
Then
distance
you
should be
you
1.
yeah, yeah, got it.
Your cosine
Yeah,
distance should output 1, right?
yeah,
So I can place some condition at the end training step that verifies that verifies if both the
yeah,
inputs in the neural networks are the same, and
yeah, yeah,
I can train it in the hypothesis function that I have. It can be 1 minus
yeah.
the, if both of them are the same, then 1 minus the output squared by 2 if I take LMS.
Yeah, yeah.
And if I have different examples as the crocodile and the football, so I can take it as 0, because if they are dissimilar, if you take cosine 90, it's not 0.
So,
So
what I was asking is that the hidden representations. Can you go to the next slide, please? Like,
uh,
no, no, yeah, yeah. So here the upper profile hidden representation, right?
uh,
So, uh, you have the output layer here is like you have to decide like what is the size of this vector, right?
yes,
So is there something like is it dependent on the number of classes that you have of image, something like this? Like if you
I don't
use
think it's
100
dependent
classes.
direct. It's, for example, if I'm training a 10 class thing for one shot learning, I don't think the output layer should compulsory consist of 10 classes, because if that would happen, then it's not dependent on that. I can keep it a 100 length vector also, output layer.
Okay, okay, thanks.
Yeah. Yeah, any other question? I'll be happy to answer anything that is in my reach.
Yeah. Hi, Som.
Hi.
Yeah. So I want to ask that this BPL model and in fact your model make use of these primitives, right? So, but humans perform one-shot classification or few-shot classification without having any explicit information about the primitives. So, do you think that humans infer it from the image itself, or I mean, what is the mechanism for having this primitive information?
Okay, so what I think is that humans learn slowly across. They learn gradually over the years. If you show a baby, if you show a 1 month baby some two blocks, and if you ask them to differentiate between a triangle and a circle, they won't be able to do that. You have seen those experiments, right? Then there is a mold in with different shapes, and there are cylinders, triangles, cuboids to put in them. So babies sometimes do
I
not perform nice in that. So is that shows that they are just born in this world. They have not been exposed to that many things. So you can, as
I
I think that
I mean I
humans
don't
learn.
I don't necessarily agree with this, because I think humans have better primitives because of evolution, right? I mean, our 10 tens of generations have already seen objects and they have an
Right.
object recognition. So we kind of have pre-wired primitives. So
So you're talking about the knowledge we have before we are born, right? We haven't seen anything.
yeah.
Yes, that does
It doesn't
exist.
mean that we are randomly set up, right?
I don't think
But
we are randomly set up. I believe that we come with a trained mind, with a trained mind. We are not dumb
Yeah.
like the neural networks. We have trained minds when we are born. But this can be used. It's like your mind cannot be evolution cannot train you to recognize a bike on day one, right?
Yeah.
So humans learn gradually, and when they learn over a wide spectrum of data, they come across many things, and that is
yeah,
something that neural
I
networks.
agree with you actually that we have some sort of primitive representations, but just the fact that we are providing explicitly information about the, maybe I'm not sure about what the exact data set looks like, but the timestamp or the exact order in which each stroke came. So that is something uh, probably not very intuitive to me.
Okay,
Yeah, but
so
yeah, great presentation, man. Thanks.
okay, so you were confused. You don't think that the strokes are a nice measure of the primitives for handwriting data?
No, I think they are excellent measures, but I mean, if you see an image, you don't get to see which stroke came first, right? I mean, I'm just
Right,
speaking
right,
in terms of,
right.
because I'm a psychology student, so I'm sort of
Okay.
more into that.
But I think you can always infer that which stroke came first, right? If given a image of a handwritten character, you can make some way out of which you can draw the same handwritten character,
Hmm.
and that
Yeah.
consists of primitives. You will, for drawing a T, you will not make a T, that you will not make such a thing, because that is unnatural.
Hmm. Hmm.
So in some way, if I'm, for example, given a Mayan alphabet, a Mayan character, and if I'm told to draw it, I will draw it using something, some form in which I know I'm accustomed to in my language. Might be that they are accustomed to some different way, and they might draw some Hindi characters in some different way as compared to what we draw. So I think that does exist. That is how I think that these are a nice measure of how primitives can be. Not the strokes. Strokes can be broken into even better primitives.
I mean, we can kind of see this if we think about not the language, but in Marathi we call it lipi or a
Yeah,
Devanagari script. I mean, even if
Devanagari
the
lipi.
language is different, but the strokes are kind of same, we tend to learn them easier.
Yes, I agree with them. Um, any more questions?
Yeah, I think if there are any more questions, you can contact Som on his ID or
Yes,
maybe
yes,
ask him. Yeah.
absolutely. This is my these are my contact details, and you can contact me wherever you want to. GitHub is not contactable. Uh, this is my Facebook
Also, the
Messenger
recording
ID.
and slides would be uploaded on BCS website. So if you want, you can check it out. If you want to share it, you can do that. It will be uploaded maybe in a day or two. Yeah. Okay, then I guess
Okay,
we'll end this. Thanks, Som. Nice presentation.
okay. Just a second. There are some things in the chat.
Yeah.
Okay. Okay. So nothing major.
Yeah. Great talk. Thanks.
Thanks for giving me this opportunity. And